Steamboat will
Because the
necessarily
people
be
that
middle,
watch Fox,
right,
see, that's
and
the only thing they broadcast for Fox
So that
News.
is one of the three
So the
properties.
people in Fox News really don't know what's actually happening. You know, because they believe, suppose that was your only news, like in.
Yeah, no, that's extra. Maybe someone to work out.
No,
I'm sorry. Oh, yeah, no,
What you lit?
I'm trying to start. Should start.
Mad that people
Three start on.
And I was.
so big. You look at murder, so you can murder.
That's what I'm on.
Not enough. Yeah.
No, but I didn't find
But
that.
you know, the people that were in July 6th,
Under a stack of
You
paper.
call them.
I looked under it.
So, you know-
Until like 5 o'clock.
like January 6th. January 6th people. So he had those people under his control.
Yeah.
So he hired them as ice. You know why they don't show them? Because most of them are some seven. How they say? No, well, it's to hide people. Yeah, thank you. Yeah. They don't want to who told us because they know, oh, you were the guy that was in January 6th. It was breaking windows, they're.
So, good day, everybody. Let me hear. Teresa is here, right? By the way, this is Anurag, and many of you might remember him. So Anurag is back in Carbon.
Hey, Anurag, what's up, man?
Hey, wow, you're still here. How you been?
I've actually just kind of come back recently.
Oh, me
so-
too.
I'll have to catch up.
Sure, dumb man.
And so you didn't remember him. Shajesh? Oh, Shajesh, of course, you know Anurag. Okay, hey.
Yeah.
And Mike, do you recognize this is Anurag?
Yeah. Oh, yeah. Yeah. Oh, okay.
Okay, so I want to wrap up everything today and let somebody else take, the spot here next time. So maybe after the thing we can talk. Oh, we have a colloquium here. Who is speaking?
Juliana Reinbold.
And the title?
I don't know the title. Something in representation.
Well, we don't.
Okay, what did I do?
Super character theory. Oh, you got that? Okay, yeah. All right, cool. That should be interesting. Okay, so let me continue, but I will first quickly review what we have done last time. One question was about spinors, where they were discovered or something, right? So I already answered this last time. Papa knew that the rotation group has like complexification, which has an extra structure, but it was like very kind of vague. I mean, it was there, but not directly spinors. But then Stern, Gerlach, they discovered that electrons have spins. So they call it spin. Now, Pauli, 27, discovered that those spins can be described as vectors in two-dimensional complex space. So this is where they were born. And they are controlled by Pauli, matrices. So the famous Pauli matrices are kind of not exactly isomorphic, but kind of two quaternions. Then Dirac came up with this is for three-dimensional physics. And the whole thing about spinors is that if you take an electron, you rotate it once around some axis with some magnetic field, it is not coming to the same state it was there. It goes to its negative value. You have to rotate once again before it's the same. And you have noticed many times, I guess, rotating an odd number of times in the bed when you're sleeping, your next day is brilliant. And so Dirac did it for four-dimensional space-time, right? So it's like a year later. And then Ehrenfest, I guess you know the very interesting story of Ehrenfest. He came up with the name spinor. So spinor as a name was born that time. And then very quickly, people realized that this is minimal left ideal of the set of matrices 2 by 2, still very, Then Weil and Brouwer they came up with a more general idea that is really coming from Clifford algebras, and this is something which should be taught by now in maybe high school or something, because they are all over the place. Like complex numbers is an example of Clifford algebra, right? And then in 47 minimal ideas of Clifford algebras, whereas this is also finished. And this is Philly brought it, I didn't. In about 2004 or 5, I came up with this idea of another spinor for smaller space, namely three-dimensional. Okay, but three-dimensional space. Okay, so what did we do last time? I introduced this group. This part is standard. These are generators of SL2Z. So everyone knows it, maybe. And generators means just take all possible products. But if you take S squared and F and T squared, no. But T S to power 3, you will get also identity. What we mean by these matrices, we understand them through the action on complex numbers, A, B, C, D. On Z, you'll be getting A, Z plus B, C, Z plus D. So this is like matrix action on complex numbers. And if you want to just understand what they do, so this is what we have done last time. It wasn't there, okay? So T simply shifts Z, adds 1 along horizontal axis. This is real numbers. Here's 1, and here is the imaginary part. So this is I. So shifts there. This one flips over this circle. So that's called inversion. What is outside becomes inside, but not only, because then it flips it on the other side of this. So it's kind of like inversion, but more complex. And then, so this is the standard thing called gamma, by the way, in very often in literature. And then, for no reason explained, we are actually from the previous semester, let's add another circle and add also flipping through this and then on the other side. And when you look what it does, it will be some matrix. I mean, that's similar to this. But then if you compose this with this again, you'll get this flip, okay? And this flip also means the same thing. You flip on the other side and then on that. So this is the group. And I thought that maybe flipping through this, plus this extra stuff, let's call it R, and let's call it F. This is easier to control because you just flip up and down, okay? What else? I should maybe write how they work. So T on Z is Z plus 1. Just use this matrix, you will see S on Z is 1 over Z with the minus. And F on Z, I think we did it last time, is I minus Z. So it's like nicely looking, while R is like fraction. Okay, so we look at this, and this bigger group is a new group, and I don't know how to call it, but this guy is called modular group. And for people new to it, just check wiki. Look for modular group. And this one, I don't know how to call it, but I thought about bimodular because there are 2 circles. And if you come with a better name, please let me know. But temporary name, okay? So that's something, keep it in the back of your head, that was such a group. Second thing is, the last time we did, I introduced spinors, but let's call them tangential spinors. How do we do it? Let's say you have 2 circles. Let's introduce your complex structure, means this is in the plane, Argand plane of complex numbers. This is one circle. This is another one tangent. And let's say this vector would be complex number, right? Because you can bring it here. The vector is complex number. Now this circle has curvature A. A is simply 1 over the radius of this circle. And this one has curvature B, so reciprocal will be the radius. And a funny thing now happens, you can define, and I don't have time to explain why, but so this is the thing. A times B times this complex number, take square root, there are 2 of them, right? So that will be called a tangential spinor this is a spinor, but this is also a vector. And all right, now this we'll mark it this way that we'll redraw those circles, and I don't draw Z, I draw only an arrow to say which direction I have taken. Because this direction will be something else, right? Square root of this number would be different. So I call it U. It will be a complex number, some complex number, and or we can think about this as a vector. So this U is in C, but this is isomorphic to R2. Okay. Now, why do I call it spinor? I explained it on this other blackboard. So in general, no, you can see it. And you can point it. Yeah, okay, yes, keep it there. No, so you see, you can take a, no.
I want to see it.
Oh, but you've seen it already last year, no? So
Yeah,
you can
forgot
just
everything.
forget about this. You have a complex number, its root will be somewhere here, right? And there are two of them actually on the other side. Both of them are square roots. If you square it, you double the angle. So now imagine that you rotate this thing once around. This one will go only to half. You have to rotate once again and comes back. So that sort of stuff behaves the same way. You have this double rotation degeneration happening there. So it could be spinor, right? And one more thing. And this is justification. If you have A, B, and C, famous Pythagorean triple or triangle, okay, satisfying this. Look at this. This is like a being on the light cone in space-time, which has 2 dimensions space and 1 dimension time. If you know a little physics, okay? So what are those Pythagorean triples? They are photons in this space. They're on the light cone, okay? And so we have a right to call them spinors. You just do through this Clifford algebra over there for this particular space, okay, stuff, and you will get that this is a good representation. This is something which is really amazing and should be also, this should be really in high school. Take a complex number x plus I y, square it, you'll get this and this. And guess what? This is your A and B, the Euclidean parametrization of triangles is right there. So the squaring of the thing. So that's why I call it spinor, tangents is spinor. But it's coming from this, right? From this. Now, why times A and B will take a long time to explain. So for today, just believe me, that things start to work when you do it. It might be looking amazing if so there are 7 magnificent theorems, let's say. They say this: if I find spinor A from this to this and call this one down the other direction, you just multiply by I. And remember, this is everything up to plus minus. Everything's up to plus minus. Next thing is, if this is spinor U between A and B, then U Q squared, norm, will be simply A plus B. Pretty amazing, huh? So like for instance, okay, let me list them all. So this is one disk of curvature C, capital C. You have A and B, 2 spinors. You can take the cross product of such things, right? X times X, Y times Y, it's like that. Like in 3D calculus, except this is 2D. This cross product will be exactly curvature of this. So this is like everything in magic. If you take a dot product, it turns out that the dot product will be also curvature, but of the circle which is going through those tangency points. Let's call it K. Okay, K can be calculated directly from like geometry. This is square root of A, B, plus B, C, plus C, A. Another application of symmetric functions. Symmetric functions, you have to talk to us about symmetric functions, it shows up here. and another amazing thing is that this is exactly the same picture by a drawn slightly differently. So if this is spinor B, well, you can always inscribe another circle there and you get another spinor if you know how to calculate it. This like heavy way, right? But it turns out that C is simply A plus B, except could be minus because you have to make sure that they are somehow agreed. So these are the 7 strangely beautiful theorems, putting some order into those spinors, okay? Now, everything really started with Apollonian disk packing, and this is Apollonian disk packing, particular one, when the curvature is 2, 2, 3, 6, 14, you should calculate, you know how to calculate. And the one outside, this is also just this, but it's going outside, so it's still tangent at one point with all of these guys. Its curvature is -1 because the minus would mean it goes outside. And this minus is important to really for things to work smoothly, okay? I calculated here using just exact positions. This is spinor, and notice that A times B means 2, 0, cross 2, 1 will be this times this is 2 minus 0, well, 2. What about, that we don't see on the picture, but A dot B would be the same thing with the dot. So 2 times 2 is 4, 0 times 1 is 0. Okay, so we know that this circle has curvature 4. Now, here is another circle, right? I can keep on. What is this here, spinor? So according to this, let me draw it here. 2 plus 2 is 4, 1 plus 0 is 1. As the spinor. No heavy work required to do, again, the whole geometry over. Now, can you calculate from this curvature? Yes, because 2 plus this, unknown x, is 4 squared plus 1 squared, according to some here. And now you have to help me. 16, 17 minus 2, 15. Okay? And otherwise you have to use this Descartes theorem to, okay? So that's it. So with this you can show a lot of interesting stuff. But recently, I mean like maybe a few years ago, I thought, wait a second, this is not really spinor as Pauli wanted. But this is complex number. This is complex number. We can associate it to it. Do I use it again? U, maybe something else. Psi. No, just let me write it. Complex number, and something which we say Pauli spinor. Like typically in physics, what you learn in physics, right? But then you can projectivize it. So this is, you can divide or multiply this by any number if you want to consider this as a vector as just projected, just direction. Divide by A. And here is B minus A. So suddenly, this, I call it tri-disk. I know, sounds awful, maybe not so awful, right? So tri-disk. You can find those two spinors, put it into this, now do this projectivization, now associated with this a single number, B over complex number. So this whole thing becomes a single complex number, okay? And okay, that's it. Yeah. Now the thing is, remember about the signs, it has to be like, they have to be agreed. If I take one of them minus, this will give you just different numbers, right? Because you want to do this plus this should give you curvature of this one with the subtraction. But if you have minus A, it will be another one which is tangent to this and this and this. Namely this one. It will be on the other side. So that's why we have to be careful. And after a lot of sorry, can you see? A lot of experimentation, I thought about this. This is the inside part of the disk. Make a path from this point to this point so that this is on your left side. It's like on the rondo when you go around, remember? And then make sure that the signs are such that this plus this would be exactly this circle or this, not the other one. Or maybe, okay. Or in other words, that A times B would give it member K. Also, if you change one of the signs of this, will be plus or minus K. Plus K is this. Minus K is this. So make those signs such that it covers that path. The other path possible is this. So in this case, you start from this, going there, and now you want B cross A to be what we want. So one of them has to be like some change. So this is like a headache, but I think this one really somehow simplifies all the calculations and ideas. Okay, so what's the idea now, truly? The idea would be, I started the idea here. So idea is this, like this is all tricycles. Try this. So things like that. Take them all, and now we have a way to send it to C through this. But there is a one problem, because here I put extra structure, namely I've chosen one of them to be kind of like anchor, and these two guys are satellites, right? You're going from this to this. Let's call it anchor. And these two guys are satellites. So you might think, okay, I want to pick up this one and calculate, for the other two. Or maybe I want actually this path as my standard. So notice how many cases do we have? 1, 2, 3 anchors, and times 2 possibilities, 6. So actually it goes to 6 numbers, to the set of 6 numbers. Now algebraize. If this is not exactly C to power 6, I want this to be like mapped into sextets of those numbers. What's the notation for it? Something like this? I think I've seen years ago like that, but I might not remember correctly.
What, so like C to the 6 modulo some equivalence, the equivalence being
Permutations, yes. So okay. So what about this? Okay, they're not scenarios. This is a set, right? But let's just draw it. Let's just draw it. Okay. Okay. So this means that you have here complex numbers. Here you have one particular guy, and it goes to 1, 2, 3, 4, 5, 6 numbers. We can call it constellation. Associated to this triple. So, okay.
I have a
Particular
question, how, maybe it's unclear to me that you would actually get 6 things there. And they wouldn't maybe reduce to fewer things by using some of your 7 theorems.
7 theorems are concerning only things like A and only B, but not this yet.
So you're starting with an anchor and then 2 satellites, and then your spinners go from your anchor into your satellite.
Yes.
Right. But are your like for example, if I would have started with a different anchor in that picture, I get 2 different spinners. So if I draw a third spinner on that picture, so you have your red anchor.
Yeah. No, I see what you mean. I see what you mean. So this is A, this is B, right? Now,
Right. So you have a third spinner.
yes, let's say like this one, or maybe like okay, like this one.
Yeah.
So now this one gets 2 in or out give the same answer, because in would be to go to out multiplied by I, both of them, the top and the bottom, so they cancel, right? So it doesn't matter. You're getting this one. Yes, you're right. And you can use now these guys somehow to
get fewer than 6.
To
get fewer than 6 on your map there.
To get 6. Because
so you've already used all those and
in order to get
everything down
6,
to get
right?
6.
So you know how to get from this spinner to this spinner, and now it looks really tiresome. Okay.
Yeah.
But like spinner, do you want to see the example or as a
No. I just wanted to see kind of where the 7 theorems fit in.
No,
You already used them
You have to use it
to their full
get it.
capacity, and now you have 6.
Right.
Yeah. Okay.
Now, the thing is that after a while, this becomes pretty complicated, right? So here's a theorem, which I discovered like too late. So I did those horrible calculations. This theorem would be somewhere, okay, it would be here. Okay, proof. Yeah, okay, proof. Proof of the theorem which I didn't say yet. So notice that this psi here associated with particular choice of A and B is what is it? B over A? B over A. As two complex numbers. Now you can, how's it called? A multiplied by A bar and B times A bar. So rationalize the denominator, right? I have to write work so you can see. We should, well, that's like hang down, right? So that's it. Now, what is this? This is A squared, the norm. And this one, after very short calculations, you will notice that this is B times A or A times B. But dot product of these guys here, like this. I can show you in a second if you want. Plus A cross B I. Okay, so if you don't believe it, do this. A1 plus A2I is complex number number 2. Now what is it? Do we have BA, right? BA bar. BA bar is equal to B1 plus B2I times A1 minus A2I. Now this is a very simple math. And now notice the real part, B1, A1, and B2 times A1, because I will be, so it will be really A1, B1 plus A2, B2. That's the real part. See this? Now, what about the imaginary part? B times A2 and A1 times B1. So let's start with A1, B2 minus A2, B1. And this is exactly what I said. Okay? So that will be that. But now let's use the 7 theorems. Let's use the 7 theorems. This thing is, let's call it C. This is A, and this is B. And remember, there's arbitrary choice of the thing. So this will be A cross B, it will be C. Right, curvature of this. And A cross B, it will be this circle, it should be red, right? And how do we call it? K. Okay, K plus this. And then A would be C plus A, the norm, right? So C plus A. Ta-da! So you don't need to calculate the particular complex numbers because this side does not depend whether you rotate the picture or not. Because you're taking a ratio of the complex numbers. So you shouldn't worry about this. It just disappears. And that's actually using it directly. You just only curvatures. So, okay, let's see, need only curvatures to get side, which I defined before. Now, you can associate easily to any, triple or tangent circles, complex number like that. Okay. And all right. Now a diagram maybe. And also the premise. We have this group, and it turns out that to get those 6 numbers, this is those 6 numbers, so constellation is same thing as the orbit of this group. Can you give it a name? No. So you see this thing here, forget about T, only S and F. That will be like flipping through this around. So notice that the flipping will give you 6 numbers, So let's call it phi, group phi. It's easy to show this as a group. Okay. Guess what? This is just the orbit of just any of them. Pick up one, Z, and the orbit of this will be exactly this. So that's something we have to, I guess, prove or at least justify. Okay. But let's start with the diagram. Okay. So we want to see how come we going through such 6 points. Actually, I can tell you where they show up. It might be interesting. Okay, if Z is here and you add with this group, so one of them will be here and one of them will be here, like every third, right? Every second, sorry, region. And this one also shows up, but on the other side. This one also on the other side. Remember this other sideness of the thing? This one also shows up, but on the other side. These are your 6 points. If you start here, but if you move it somewhere else, it will like maybe more interesting. And I have somewhere maybe pictures. And so this we need to prove, right? Do they write it somewhere? Yeah. That's a kind of simple theorem. Okay. So to see why it works, this is a diagram which I think is the easiest to follow among many of them I wrote. So let's say this is A, let's say this is B, this is C, 3 tangent mutually circles, sorry, disks, okay? So, and this will be the path. This path will give you immediately a complex number. How? You don't need you just need this here. You use those 3 things. And first you have to calculate that thing. So, you know, so somewhere here we need K equal to that. Okay, so it's just you need curvatures. Okay. So this is one. Now you can go down and go from here to here. Again, you have to go, remember, with your left hand inside the disk. So that's another path. Okay. This is still CBA. So I'll tell you right away. It turns out this corresponds to, for the side, it will be this action of S. And I think this I showed last time. Stay there. So, okay. Another thing would be going to another path. Let's say pick up this as an anchor and A, B. So if this is an anchor, you're going with your left-hand side. So it will be like that. So, okay. And if you use S, then you're getting A, B, C. This is an anchor, but going this way around. And I tell you right away, this arrow, you can do it with the F composed with S from the group. And we have to see it. This one goes both ways, right? This is like evolution. And F beyond, okay. Now, this is then SF. Notice if you multiply them, you get identity, right? Fs times SF. This is identity, this is identity. So, okay. And so you have already 5 of them. 4. So what is the next one? So notice I put it like this. You're going this, and then down. And finally stop to be a total mess. This one, right? This is anchor, and this is also going FS, and that way SF. Here S, and that would be like that. Okay. Now this place behaves this way. Fs is going backwards. Okay, and this one is going backwards. And of course, if you go to the next one, you should come back here. So I could put it into a different diagram, more like 1, 2, 1, 2, 3, and then here's another 3. So maybe going back out, this, this. But then when you put those arrows, it is really messy. So it should be this, but it kind of doesn't work nicely. So I'm using this. So you're going still farther, and I'll couple the couple, or maybe like this. Any musicians here? Please go around. Okay, that's it. So we have one number, but then by action of this group, you get in all of it. Now, should I? So is that clear? Any question? Question will be, how do you know, right? It works this way. Which one we should prove? So maybe you should take like one particular example and do calculations, huh?
Explain the difference again between the top one and the S transformation, because the arrows seem to be in the same direction.
One direction. So S acting on this will be this,
Okay.
and to get there, you just apply S once again. So S squared is identity.
Mhm.
That's what your question.
Should
No.
they be opposite directions though? They're the same direction. The arrows.
Oh, here.
No, like between the top and that one and the bottom one.
So this means S goes this direction, and also this is you use the same
Yeah, I
one.
meant the arrows like on the anchors.
Oh, this goes like this,
Yeah.
and this goes like this. No, you
all
have
the way
to,
around. Okay. I
yeah,
see.
okay, so,
I didn't know that.
so to keep things somehow, at bay, always walk on the edge, but so that your left hand is inside the circle you're looking at. So you see here, yeah, so you're going like that.
Okay, sorry, I didn't realize they said.
No, you're right. I mean, at the beginning, I did those calculations. I take all of them possible and so on, and turn out that now you should really put some rules.
Never
what's-
drive into oncoming traffic.
So the top one, which circle are you going around then?
Here,
No, on the top right, on the top left,
on the top
that
left.
he was talking about.
Yeah, it's
So
there.
that one, what circle
Oh.
is that one going around? If that one's going around A,
That's also
They're
good.
both around there.
they're both going all the way around A.
Yes.
Oh, okay.
First one's A.
So now this and continue, and then here.
Well,
We didn't draw on the beat, but.
it just makes me wonder with his question, because it does seem like it, because no, because it just seems like what he said is that you're going around the same way on
You are,
both of
yeah.
those on the left.
You are.
You
On all of them.
In all of them.
Counterclockwise all the way.
Path, so you get a different curvature there.
Yeah, they're all.
It's a way to partition
the
path of the
Well, that I get, but
Yeah, you can say clockwise, but
that's not what I'm
except,
asking.
ask again.
Yeah.
Based on what he was saying, those two things on the left seem like they are the same picture.
No, because you're walking from this point to this point, and here we're going from this point to this point, you change.
Okay, that answers my question.
Yeah.
That was, okay.
So let's say here's an A and this is B, that if you go back to Spinner's description. So what would be associated number? It will be B over A, if you remember, the one to which you go over the one you started. Now, here, if I draw these two guys, arrows, if I multiply them in the same order, you will get minus.
Right.
Because for them to be agreed, so this is really this new side, say prime, would be negative A over B, and the other way around because you change the order. And when you compare them, you see C prime is 1 over psi with a minus, and that's exactly what S is doing. If I wrote it somewhere, here.
You did, yeah.
Yes. Okay. So we know that this S is part of the group.
Yeah, thank you.
And then this one, we can show this one if you want. Yeah, let's go quickly. So, this Fs on Z, what is it? S is 1 minus 1 over Z, right? And F is I minus this, so it will be I minus this negative thing, like 1 over Z.
Should be plus.
Plus, yes, minus with minus. That is meant when I said minus. And okay, so let's calculate where, maybe here. So F as on particular thing, like 1 over M, I call it K, right? K. K plus CI over A plus C plus I. Okay, is this there? I think my notes, I decided to do SF. Okay, SF. SF, you have to do it the other, order. So 1, and here Z minus I. It's I minus Z with the minus. Okay, I changed the order of the thing. It will be quicker to calculate maybe. So SF of one of them, which is where A and C. C is the anchor, so it will be this one. See, and starting with A, so that's the one. That's the associated number. Add I, take the reciprocal, and claim is we should get this one. So let's do quickly the calculations. Common denominator. So K plus CI plus I times A plus CI. Oh, minus and minus, right? Minus Leonard. We talk after. So CI, right? And then upstairs simply A plus C. Right? I just removed the thing from the denominator. Now this is gone. So let me repeat it. A plus C, and here is K minus IA. Well, it doesn't look like that, but we can again rationalize the denominator. So it will be A plus C times, okay, K plus AI. And downstairs, if you multiply by the same thing with plus, you get K squared plus A squared. A squared plus A squared. Still doesn't look good, but let's keep the top still untouched. Okay, and but what is K squared? K squared is, remember, AB, BC, CA. It's a symmetric function of those three guys. So it will be A squared, no, A, B plus BC plus CA plus A squared. Now, in these guys, you see this guy? You can factor out A, and then you will have C plus A. Calculations you always hope you never do again, right? So here B is common factor and A plus C.
Wow, what bigger.
So this is common thing. Will be cancelled with this. So you have K plus AI, and then A plus C, right?
B.
Yeah, A plus B.
Yeah.
Okay, cool. Be fair. We get exactly this. So it goes FS. Now notice that FS is one of the generators. You can always change F into SF because they recover the original. So like call it end of the proof because the rest goes the same way. So that's it. Now, all right. So this constellation is given by this subgroup. But we have a bigger group, and the bigger group shifts every complex number to the next one. Does it do anything for us here? And the answer is, oh, before I do the answer, we have achieved here something, namely, since you see they're like, you can pick up for action of this group, one of these regions as your fundamental region, and everything else is just, you can get it by the thing. So for instance, you can pick up this. This means all possible tri-disks, all shapes, small, big, up to a shape, are here. So this is parameterization of all tri-disks. And these guys are just, extra stuff in a sense, right? So if you divide C by the action of this group phi, all tri-disks, I still don't know. So that's the kind of space of all of them. But we have this extra thing, we can add one. So let me add one, because adding is easy, right? Supposedly. I'll make sure I'll do it wrong. Okay. So the quickest way to get there. Okay. So let's start with a particular A, B, and C. Okay. Let's see, this is A and this is B. Let's go back to the tangency spinors. Okay. And then, so our Pauli spinor will be AB. And we know that we associate with this just simply B over A. This was explained there. And let's call it Z. Complex number Z. Now, what about this circle? I mean, this is a tri-cycle, try this. But you have another one by putting this one here and removing that guy. So squeeze this in, okay? You have a different system of spinors. This is A, and remember this one? A plus B. Okay, so in this case, we have A, same direction, okay, of the path, right? So A over, and here A plus B. So with this, we associated the bottom over the top, A plus B over B. Over numbers.
Or A.
Over A. Okay, and do you see this? Z plus 1. You. Yeah, thank you. No. There you go. I wouldn't do it without spinors. So you see, so this move makes a new one. And now, how do you get all possible No, let me remind you that you start with any tri-cycle, try this. Well, if you keep inscribing, you get one of the Apollonian gaskets. So by this move, you get them all. You just add one, apply one of them to just rotate, change the anchor again and again and again. So, but that's it. So this move, it is like the inchworm. Have you seen an inchworm? It's called also geometer moth. And for people who've never seen it, if this is a leaf or a stem, legs. It kind of like walks. That felt, I've seen it before. So they call it geometer moth. And the caterpillar, that's the funny motion. So that's the kind of caterpillar moth motion or inchworm motion. You just remove this and put there. You can remove this one and put this one, or remove this one. You see, this is like the tricycle goes through all possible tricycles in this particular one. Okay. And now, in just 1 minute, I'll just tell you one thing. Just resolve the extra stuff here. These are all possible tricycles, but the tricycles with one of them being on the negative side, this is the case where you have tricycle of this form. Okay, they are all in this place. So in the sense, all these points correspond, every point to one particular Apollonian gasket. So these are possible tricycles. So C divided by Xi is all Apollonian patterns. Okay. Sure, English, but I know that I didn't explain everything in details, but I can just wave to you with the pictures. So,
So you, if one of them is flat, so that
Mhm.
is, if one of them was flat,
oh, like this one, and
yeah,
this is a tangent to it,
so then A
and this
would
is
be
tangent to
zero.
it, it would be a tricycle. This is one.
So what happens in that case?
Everything works. I mean, it will be somewhere here close to the center. Actually, I drew something like this for all tricycles. You have like a magnifying glass or something. Here is the like a this Apollonian gasket. Your thing is right there. It's also included. No cheating. No cheating. Okay. And I try to draw like pick up so-called integral packings. Integral packings is like this one. All numbers are integers. So well here I instead of this I use this because you can always flip it over. So that's a picture. Yeah, a very strange picture. It's like a beautiful fractal, right? Mike asked me last time whether eventually, if I drew all of them, would they cover the whole thing? Yes, all the rational numbers would be covered, but the order they show up, they make like this beautiful thing just in case you want for summer or your t-shirt or something.
Yeah.
50 cents per. And I think I have some other pictures. Okay, that's it, because you have the talk in a few minutes, so we need a break. So thank you very much. Let me remind you that we will run maybe like meetings where I explain that's not that stuff, but much more about the Polonian gasket from the very, very beginning, starting with the Descartes famous equation and build up. And what is amazing, I think I wrote in the letter, so many things, so many structures, mathematical structures you learn in physics, but they show up here, like spinors, Minkowski space, for instance, is hidden there too. So we can discuss it rather than I can present, but we can look for some nice, problems. And remember, there's one puzzle. How would you describe those? The group generated things not by generators, but some conditions. So, like for instance, only this part, you want the determinant of the matrix to be 1. But if you add this is bigger. It includes also the Gauss integers. But is there anything tying in only to this group? I don't know. Maybe some, I don't know, symplectic structure maybe or something. I really don't know. Okay, so next time we have a few propositions, right? Can you maybe talk someday about your work?
I can probably towards the end of the semester, if that's okay.
Okay, you don't need like much preparation. Look at me.
Yeah.
So,
It's very nice.
so because so it's just just tell us what you're interested in and what
Sure, yeah.
and just make it like sort of accessible. So even I can understand it, okay?
Yes, of course, yes.
So you can talk even tomorrow, right? Or no? Because you know what to do, yeah. I already forgot. Okay, if not now, maybe later. It's up to you. Later, okay? Anybody else like ready for the next week? Philip?
Not yet.
Symmetric functions. Please explain why they're symmetric.
I mean, I could say something about it.
Okay, anybody else? Mike, you had like a lot of free time or something.
Oh, yeah.
So,
If the expectations are not incredibly high, I can talk about loops of
Yeah.
bull Mufang type, and then I can show some work I've done.
with examples.
Yes, with pictures and stuff.
Picture good.
With pictures and stuff.
Okay, so let's do it this and please think what you can, offer.
I might need to use the TV or something for the pictures.
Okay.
They'll take a while to draw, but
Okay.
yeah.
Oh, you could just wait. Okay, so thank you. Okay. So send me a typo. Probably before Monday.
Okay.
Yeah.
And everybody else, please think what you want to offer. Now artificial intelligence is such a big thing. We expect you to explain to us why it will never work.
You're, can I have a minute first? Well, we haven't corrected.
Oh, yeah.
That's fine.
Oh, this is important.
Wait,
Did promise us this.
You have
and I
class?
did it.
Yeah.
Okay, just
Mandatory
quickly
attendance.
show you. Okay, next time.
They're going to have a
You know
small
this guy.
And there's coffee in
So
the
this is.
room.
They're going to have a small celebration.
Really? Don't forget.
Okay, I'll stay.
Next time you go.
Are your spinners genuinely members of some left ideology?
Yes, yes. Of this space.
I didn't
art.
email.
you know,
But I'm all surprised there today.
Cliffordize that and then complexify the Clifford algebra. Grab the minimal left ideal and you get your
More or
spinners.
less.
Are
you free?
Okay.
Not tonight, it's my anniversary.
It's even better. Much better time.
Well, so
We got an Olive Garden gift card. We're gonna
I guess
use
the
it
way I
to-
understand
Yeah,
the
so,
spinners is start
are
with
you wanna like get a beer?
space, say R21,
Yes.
right?
Yeah,
As your
are you-
Clifford algebra.
Yeah.
Whatever.
Uh,
I have.
what,
You
you
can
figured that out?
complexify it first.
Oh, well, not necessarily. No, no.
no.
So that
The thing is that you get triple algebra.
I guess I can message you on Messenger.
We can help you.
Explain matrix representation
What
Yeah,
homework do
me
you have?
neither, so.
of those elements. of
It's
the-
easy, what's up?
And as a matrix.
I don't know how much help.
How you doing?
You know what, the only,
Space, it acts on our spin.
oh my gosh.
And then why is it left idea?
Yeah, Patrick's Ricky, so I think he's still around.
Oh, you know, I saw him. Like, out it somewhere.
I did, have like, me and Thomas, about Thomas.
Now,
Oh, yeah, you were. You
I
should.
thought you were saying plus minus one.
working at project part-time.
Oh.
Like sign.
Yeah,
And he was working there.
Yeah, you were.
That's what you got.
Yeah.